Let's look at some more advanced trigonometry now. This is where we move on from what we learnt at GCSE. So we're going to have a look at this right angle triangle, a general angle theta, and we're going to call this length here 1. So 1 unit length, and that means that using SOHCAHTOA, sine is opposite over hypotenuse, but as our hypotenuse is just 1, that tells us that sine theta is equal to the opposite over 1. So sine theta is simply the opposite, sine theta. We can apply a similar argument for cos to see that this length here is cos theta. Okay, so now that we know that we have sine theta is the opposite, cos theta is the adjacent, that's fine. It kind of allows us to see what this would look like for a right angle triangle. We know that the opposite is sine theta, the adjacent is cos theta when we have a hypotenuse of 1. The trouble is, so far we've been restricted to angles of 90 degrees. And you've seen that sometimes, especially with the sine rule, we want to use angles which are greater than 90 degrees. So how does that square with this definition of sine, cos and tan in terms of a right angle triangle? So what we're going to do is we're going to extend this. We're going to actually put this inside what we call the unit circle. So we put it inside a circle. We call it the unit circle because it has a radius of 1. What this allows us to do now is it allows us to rotate it round. Let's imagine that we actually position this on the set of coordinate axes. So we've got our x-axis and our y-axis. This now allows us to keep increasing theta beyond 90 degrees. And what we're going to do is we're going to think of sine theta as the height, the y value, and x as cos theta. So we're going to say that the y value is equal to sine theta and the x value is equal to cos theta. So what happens is, as we increase theta, let's say that we now put theta over here somewhere. So we're always going to measure theta from the positive x-axis around. You can now see that in this second quadrant, theta is obtuse. It's greater than 90 degrees, but less than 180 degrees. And we still have a right angle triangle if we draw it in the appropriate place. Remember, our circle has radius 1. This height here we'll still define as sine theta. This width here we'll still define as cos theta. But what this tells us is that as we enter this second quadrant, i.e. as theta is between 90 degrees and 180 degrees, sine of theta will still be positive. We've still gone up on the y-axis. However, cos theta will now become negative. It will be less than 0. Okay? If we think of the graphs, that explains why sine theta increases. So as we increase theta, the y value increases and increases and increases until we reach 90, which is where we have a maximum point, and then it starts to decrease again until it reaches 0 at 180 degrees. If we continue to increase theta, now we would enter the third quadrant. The height, the y value, sine theta, would become negative, which is why our graph drops down there. Continuing to increase it into 270 degrees, we reach a minimum point of -1, where we're entirely downwards, and then we start to increase again, approaching 0 from below. A minimum of -1 and a maximum y value of 1. And that's how we generate the graph of y equals sine x, or in this case, sine theta. That's how we can use something which is usually thought of as related to triangles, but we can take up to 360 degrees or beyond by continuing to just rotate round. And it explains how sine theta can be negative and how we can define it for angles over 90 degrees or over 180 degrees. A similar argument does work with cos. If we look at cos theta, or y equals cos theta, for an angle of 0, it was entirely made of x component, so it had a length of 1, and then that x component decreased until we reached 0. Once we're at an angle of 90 degrees, the x component then became negative as we continued to go round until we reach 180 degrees, when it's at -1, its most negative value, and then it starts to increase again until we reach 0, no x component at 270 degrees, finally increasing until we get back to 1. So that x component is increasing the whole way along here until we reach 360 degrees. When it finishes, it comes back up to 1. We could continue to oscillate round if we wished to get bigger angles, but again it reminds us that sine and cos are defined in terms of a circle, not in terms of a triangle. This becomes a much more useful definition at A level. Okay, so let's just clear this off and we'll go back to that original sketch and we'll see what else we can do with that unit circle in the next video.